double chevron, top right.
Yes.
The double chevron. There should be like a presentation there. Yeah, presentation. Okay.
No.
Good.
Well.
So, 5 past. So I'll give you a 5-minute sign.
It's more.
Yes.
Thank you very
Thank
much.
you for staying.
It's a joint work with Foret, the University of France. In fact, I want to give you some extensions of what we call categorial dependency grammars. CDG, categorical dependency grammar, were introduced by Alexander Dikovsky years later. And well, we have some problem using non-projective dependencies for this categorical dependency grammar. I can show you, in fact, the problem with natural languages. Here we have a sentence that corresponds to I have told him that he has returned the book in French. And the normal analysis say that we have a critic that corresponds to him, and this critic must be before the verb. You can see we have a non-projective dependency between the verb G, talk, to the critic lui. But if we have something more liberal from the point of view of non-projective dependencies, it's possible to have another analysis, which is the second one here, a wrong analysis, where, in fact, the first verb that has this dependency, but it's the second one. C'est aujourd'hui that corresponds to return the book. And of course, we don't have those kind of false analysis, because well, it's something very, very strange to have this critic very far away from the verb that corresponds to it. So what we want to do is something that blocks, in fact, the possibility to have such a non-projective dependency somewhere between the verb rendu and the critic. And to do this, in fact, we introduce a new system which is called the typed barrier in CDG to reduce this possibility. The second problem that we have is that with CDG, we don't know if this class of languages is closed using the clean plus operator. In fact, there are no result for this. And our solution to that is also the same thing, the typed barrier, and we will see that it's possible from CDG with extended with typed barrier to have such a result. So now I want to offer some background on CDG languages. After that, I want to give you some interesting in the product of CDG languages, how we can define the product of two languages using this framework. And in the first step, I want to show you our proposal, that is the CDG with typed barrier, and the application of this CDG with extended with typed barrier to the clean plus of CDG typed barrier language. After that, I will come back to the initial problem that we have with natural languages with the sentence as given in the second slide, and I give you the conclusion after that. So, what is categorical dependency grammar? In fact, it is something that wants to modelize surface dependency structures. Of course, it is a notion which is well known. It's just a relation between two words with a name, and also with an orientation that can be on the left or on the right. Here we have a sample sentence. This deals with more problem than profits. And we can show that we have two kinds of dependencies. The first kind of dependency are projective dependencies. The projective dependencies are shown using plain arrow. So here we have 1, 2, 3, 5 projective dependencies. We have also non-projective dependencies using dashed arrow. And the difference between projective and non-projective dependency is that for projective dependency, it's not possible that one dependency cross the other. You can just look at that. If you remove this non-projective dependency, the rest is completely projective, and it means that there are no crossing between the arrows. For non-projective dependency, we have a second system, in fact, in the grammar, that can allow non-projective dependency to cross other dependencies. So now, how we can have these two systems, in fact, in the categorial dependency grammar, in fact, we have two parts in the type associated to the words. We have the first part that corresponds to projective dependencies. This part is relatively classic when we know categorial grammars. In fact, we modelize the dependency between two words using a positive valency on the governor and a negative valency on the subordinate. For instance, the dependency between broad and here corresponds to a positive valency associated to broad and a negative valency associated to here in the two types of these two words. When we have all those balances, we can create projective dependency when we saturate, in a sense, the balances of each word. For non-projective, an important thing is that what we have here is a principle that, in fact, the two words, in a sense, must be adjacent. It's this principle that says that projective dependency cannot cross another projective dependency. For non-projective dependency, it's more liberal in a sense. So we have also a positive valency and a negative valency, but the connection between the two words are somewhere in the left or somewhere in the right, and it's possible way to modulate something that can cross the other dependencies. Now we can shift to the typing of the words. So for the word, in fact, we have projective dependencies that to modelize projective dependencies, we have classical categorial types that correspond to an head of the subordinate. This is the head type of this type. And we have for the governor a left part that corresponds to the left subordinate of this word, and a right part that corresponds to the right subordinate of this word. So, for instance, we have G that corresponds to a right part or a right argument of the word that corresponds to this type. In type, we also have second part, which is the key that we have here, and those two types correspond to the non-projective valencies of the words. I will show you this part in a few slides, but starting with only the projective dependency valencies, we can, for instance, have something that corresponds to this sentence. The lexicon is there with only solidity for projective dependencies. And if you know categorical grammar, it's relatively easy. For instance, for word, we have the actual center in the head of this side, and we have an argument on the right, which is the present dependency, and an argument on the left that corresponds to the C tuple dependency. It was as a subordinate on the right and as another subordinate on the left. At the end, we have in fact S that corresponds to the axiom, correct sentences. For non-projective dependencies, the system is quite different. We only have, in fact, polarized balances. As you can see, in fact, in time, there as an element that up on the top of the type, and we have only the positive balances or the negative balances, and no more question of what is a head and what is an argument. So it's kind of something which is more liberal than the part corresponding to projective dependencies. A small example, Disney wrote more problem than Flokins. We have in the lexicon the right part that corresponds to the projective part and the red part that corresponds to the non-projective part of this sentence. And you can see that, in fact, we have only one non-projective dependency between more and than, and that corresponds to the two polarized balances that we have. One in the nor and the other corresponds to that. So now, what is the calculus that we use for this calculus? We have the traditional eliminator of categorical grammar. If we have the category C and we have category C above beta, we can eliminate this category C and just have the category beta. The polarity here is just the concatenation of the two polarities we have in the few topics. And this time we have a new dependency, between the two words that correspond to the two groups. We also have something quite strange. If we have a type which has an empty head, we have something that just disappear the type, and of course there's new dependency in this case. We also have something that can iterate an argument, correspond to a C star here. So when we have a C star in the governor, it's possible to link this C star with 0, 1, or several arguments or subordinates using the two rules that we have here, he and here. And finally, we have a rule for the non-projective dependency that correspond to polarized balances. Well, in the polarity, we must have something that corresponds to a positive balancing, and a corresponding negative balancing with the same name. Of course, there is a rule for this, is that for the P that we have there, we must apply the first available rule. It means that in P there, it's not possible to have other kind of polarity of this name C. That is, we mustn't have those symbols there. So P don't P has no occurrence of those two polarities. Now, if we have a lexicon like this one, we can deduce the fact that John ran fast yesterday is a sentence which is correct in this for this grammar, by finding a derivation starting from the type of different words. So we have a derivation there. And from the derivation that ends with the axiom S, we find a dependency structure that corresponds exactly to the derivation. We only have the dependencies. So we have here only projective dependency, but of course it's possible to have non-projective dependency. Here we have the other rule, the left part, the left rule on the right rows. Quite different from what we have naturally in the categorical grammar, because traditionally it's only the first rule. Here is an extension that corresponds to the empty head, and also for the star operator. And the last one there corresponds exactly to the non-predictive dependency. Here is a language which is recognized by categorical dependency, which is a mixed of three symbols A, B, C, but of course we must have the same number of A, B, and C. The lexicon is there. You can see that A is associated to several types, B and C also, but only two for B and only two for C. You can also see that, in fact, we have empty heads for the type B and C. It's possible to have CPG with something that forbids, in fact, empty head, but well, this one is more simple than this kind of language.
So does this match exactly those strings that have any number n?
Yes, any
equal and any
just have
order.
the same number of A, B, and C.
So it could be 17 of each, and in any order.
In any order. It's not a context-free language.
Yes, no, but
So now I want to give you the problem with the product of CDG languages. Here is a derivation for the example where n is equal to 2 of the language EN, BN, CN, a list of A, then a list of B, then a list of C, but we have all the same number of A, B, and C. The lexicon is there, so we have two types for A, two types for B, and two types for C. We have only one non-projective dependency A, which is D. The rest is just classical calligraphy. As you can see, in fact, the derivation corresponds to the part that we have here a list of A with some pixels which are the balances. We have the negative balances that we have there. Here we have something for B and T that correspond to parentheses, very similar of what we have in context-free language. Context-free language corresponds to a big language, for instance. At the end of this thing, what we have is a list of polarized balances there, and we must check that each polarized balance corresponds to the dual one. This one must correspond to this one, and after we have eliminated those two polarized balances, we have also a couple of two polarized balances, positive and negative. At the end, we have this axiom S. So we have to see that corresponds to the analysis of EC, BB, CC for n equal to 2. If we want to go to the dependency structure, it's also possible. From the derivation, you can deduce the dependency structure. In fact, I see that there is a mistake on this structure. So now we want to create the product of two CDG languages. Well, in this case, we just take the language EN, BN, CN, and another with itself, means that EN, BN, CN, with EN, BN, CN. And what we have is something that corresponds to a first EN, BN, CN, and the second one there. Of course, P and Q greater or equal to 1. So how can we build such a product? The first idea would be to have something that looks very similar to what we can done using categorial grammar. That is, in fact, we just need to duplicate the axioms. We have the first axiom, which is S, and we duplicate it with S2 and try to link the first axiom to the second axiom. So it's something very can show here. So the first axiom S has a subordinate, which is the second axiom S2, and the S2 has the same structure as the S as the first axiom. But in fact, it doesn't work with CDG because for non-predictive dependency, it's possible to have something that make a wrong example. Sometimes can check that E, B, C, A, B, C is in the language corresponding to this grammar. Well, you can see that we have 2A, 1 C, so it's not good for ENBN yet. And here we have only 1A, 2B, and 2C. So it's not also the proper language for this part of the word. And it's due to the fact that it's possible to have non-projective dependency between this part of the word to this other part. So it's not a good idea. The good idea, in fact, is just to create, in fact, two grammars or duplicate all the types using the index 1 and the index 2. And what we have is the first part, the left part of the word, that introduced the second axiom, S2, and the second axiom corresponds to the second grammar. Now it's not possible to have an interaction between the left part, the right part, and the left part because, as you can see, all the valences, all the polarized valences, T2, are linked to the second grammar, and T1 here are only linked to the first part, the first grammar. So it's not possible something that corresponds to both sides. But now I want to show you something that is, I think, better is CDG type barrier. And for the same problem, we'll show that it is very easy to make a product or to make the clean plus of CDG language. What is the difference between CDG or classical CDG and the solution that we have here is the introduction of type barrier, which are this symbol there, the vertical arrow with a name C. And we only charge, in fact, the first available principle. It means that when we check P there, P has no occurrence of both the two polarized valency, but also no occurrence of this vertical barrier there. And this barrier can, in fact, just cut the possibility to have non-projective dependent between right part and left part of the type. And if we look at the first solution that I give you for the wrong solution for the product of EM, DNCM with itself, it's very simple to have the same grammar. We just add a barrier there, the first type of A, and everything is perfect. We have this barrier there that indicates the possibility to have a non-predictive dependency between this part and this part. And also we have exactly what we want, that is EM, DNCM product with itself. It's also the same thing for the clean plus, for the same grammar. In fact, we have very similar grammar for this, the clean plus of EM, DNCM. The only difference is there we have SS, S, and which is different from the previous grammar, which has S and S2. You can see that this is the clean plus, and for the product we have S and S2. So it means that here we have only one element after the S. Here we have a certain number of applications of the grammar. If we are intruding with the clean plus, in fact, the transformation that start with a CDG with barrier to the clean plus of the CDG, of this CDG, was 5 steps. I think I won't have time to show you all the steps. Well, can be presenting in articles. So I want to finish using the first problem that I mentioned, which is this example with the sentence "Je lui ai dit." I have told him that he has returned the book. With the problem of the click in. This one is the normal analysis, and this one is the wrong analysis. So we have the non-predictive dependency there between the verb rendu and the predictive with the typed barrier. We can limit, in fact, this non-predictive dependency using a barrier somewhere. In this example, I put this barrier on the verb dit. And this barrier inhibits the fact that we can have non-predictive dependency on the RP, and we only have one solution, which is the normal analysis. Conclusion. Sometime, in fact. So with the CDG extended with typed barrier, we modelize relatively easily the product and the clean plus of CDG extended with typed barrier languages. We have also no parsing complexity penalty with these two constructions. And the result, in fact, is that what we have for this class of grammar is an abstract family of languages. So what is an abstract family of languages? It's a class of grammar or languages that are closed under union, product, clean plus, heteron-free homomorphism, inverse homomorphism, and intersection with regular sets. In fact, the same question remains open for classical CDG, so don't. And I want to show you that it's possible to use this typed barrier also for natural languages. And control the range of specific non-predictive dependencies. Thank you very much.
Couple of quick questions and then lots of questions with coffee. Yes, please.
It's very fascinating. So I'm more used to dependency parsing with universal dependencies, and there they do it in a different way. So there is no grammar, but you have a tree bank, and then you learn parser by machine learning. Good. Or have you looked at if one can learn these rules also from the tree bank?
You mean the type and dia or all
The kind of rules that you are using for parsing?
Yes, we have some paper about it with Denis Foret.
Yes.
Well, for universal tree banks, we have some more results.
Yes.
We have also other results using different corpora. And of course, the problem is that is it possible to have something very rich? If we have something very rich, like a dependency structure, the problem that we have for CDG is that we have two kinds of dependencies.
Yeah, they only have one.
So the PhD student some time ago tried to learn if it's possible to select if this one is a projective one and this one is a non-projective one. And another one, perhaps it's something that can be done to solve this problem. Questions?
And I have one very quick one. These barriers, I mean, I can see where they should go in your example, but when you're designing a grammar, does it feel natural to know where the barriers should go?
You can choose the way for the problem of inputs and predictive. So there is an algorithm that can give you where you have to put variance. Of course, for natural languages, it's more complex.
Yeah, that was my question.
Yes. Here I choose this word from this barrier because in fact it is a barrier for critics. It's a specific barrier, not a barrier for everything. So I choose this one because this verb, in fact, is very similar to the other verb. They are exactly the same arguments, a subject, an accusative object, and a dative object, and both, in fact, can have the critic using a dative clinic. So it's why there is another possibility to say that each part of a complex sentence can be, in fact, separated to the other. In this kind, it's possible also to have something there with the word that corresponds to the relative. So we can also have something on different. So there are different possibilities.
Okay, let's thank the speaker again. Copy now, and we reconvene here at 4.
In your example, some is the claim was that they differ not